Good day everyone, my name is Leslie Daniel B. Ahok, an electrical engineering student, and today we are going to solve an AC circuit problem, specifically problem 5.12 from the book of Johnson Johnson and Helborn. In the original circuit, I first assigned the impedances by converting all the resistors into their complex impedance form. We are asked to find the voltage V using superposition if the impedance Z is equal to 2 plus J3. Let us begin by finding the voltage due to the 6 angle of 30 degrees ampere current source acting alone. Since the current source supplies current to parallel branches, we apply current divider rule or CDR to find the current flowing through the branch containing the impedance of 2 plus J3 ohms. By doing CDR, we have I is equal to the current source, which is the 6 angle of 30 degrees, times, for the numerator, the conductance of these parallel combinations, and this impedance 2 plus J5 ohms are in series, divided by the total conductance seen by the source. Solving the current by CDR, we get 2.118 angle of 38.128 degrees ampere. That is the current that flowing through this impedance 2 plus J3 ohms. After getting the current, we multiply it by the impedance of 2 plus J3 to obtain the voltage 1. By substituting the current we computed earlier, we have V1 is equal to 2.118 angle of 38.128 ampere times the impedance 2 plus J3 ohms. We get the value of V1, which is 7.637 angle of 94.437 degrees volts. Next, we return to the original circuit and consider the 10 angle of 30 degrees voltage source acting alone. Using superposition theorem, the current source is replaced with an open circuit and the other voltage source is replaced with a short circuit. Now simplifying the circuit, the impedance 2 plus J3 ohms and 2 plus J5 ohms are in series. We combine them. 2 plus J3 plus 2 plus J5 is equal to 8.944 angle of 63.435 degrees ohms. The series combination is then parallel with 6 plus J2 ohms. Solving for that parallel combinations, 8.944 angle of 63.435 times 6 plus J2 all over 8.944 angle of 63.435 plus 6 plus J2, we get 4 angle of 36.870 ohms. After finding the equivalent impedance, now we see the two impedance connected across the voltage source. We apply now the voltage divider rule or VDR to compute for the voltage or V2. So by VDR, we have V2 is equal to the voltage source, which is 10 angle of 30 degrees, times the equivalent impedance, which is 4 angle of 36.870, all over the total impedance, which is 4 angle of 36.870 plus the 4 minus J2. Computing that, we have V2 is equal to 1.665 angle of 33.69 degrees volts. As you can see, the resulting voltage has a negative sign due to the assumed polarity directions. Yan. That is the polarity. That's why it's negative. And again, for the last part, we go back to the original circuit and now consider the 20 angle of 45 degrees voltage source acting alone. Applying the superposition theorem, the current source is opened and the other voltage source is shorted. Now simplifying the circuit, the impedance 4 minus J2 ohms and 6 plus J2 ohms are in parallel combination. So we compute for the equivalent impedance. We have 4 minus J2 times 6 plus J2 all over 4 minus J2 plus 6 plus J2 is equal to 2.828 angle of negative 8.130 ohms. And then we apply the voltage divider rule to find the V3. So V3 is equal to the voltage source, which is 20 angle of 45 degrees, times the equivalent impedance, which is 2.828 angle of negative 8.130, divided by the total impedance seen by the source. So we have 2.828 angle of negative 8.130 plus 2 plus J5. And now we get the value of V3, which is 5.54 angle of negative 11.312 volts. And finally, we go back to the original circuit. By the superposition theorem, the total voltage is the sum of all individual voltages. V is equal to V1 plus V2 plus V3. Substituting all the computed values, for V1, we have 7.637 angle of 94.437 and plus for V2, which is negative 1.665 angle of 33.69 plus V3, which is 5.54 angle of negative 11.312. We obtain the final answer for the voltage V. We have 6.584 angle of 58.336 degrees volts. That's all for today and thank you for watching.